In the previous video, we saw the fully developed laminar pipe flow and derived a formula for the flow rate through the pipe in relation to its pressure drop, the diameter, and viscosity. In this video, we are going to look at turbulent pipe flow, where let's say we have a flow that has an average velocity of V bar and flows across a pipe, and the fluid has a density of rho and a viscosity of mu, and the pipe has a diameter of d. Now, based on these quantities, rho v d over mu, one could calculate what is known as the Reynolds number that compares the inertial forces on the fluid compared to the viscous forces. Now, I can write the Reynolds number as which is rho v d over mu as rho v squared divided by mu times velocity divided by d. Now, what is rho v squared? Previously, we saw that rho v squared is a measure of the dynamic pressure, or it is related to the inertia of the fluid. Rho being the density, v being the bulk velocity. Rho v squared is the energy per unit volume that's associated with the inertia of the fluid. You can also write this as energy per unit volume. That is every meter cube, every centimeter cube of the of the fluid moving at a velocity v has an energy of rho v squared. Rho v squared is the energy contained by every unit volume of the fluid, and this energy is associated with inertia of the fluid. Now, what is mu v over d? If you think of the pipe flow, here is your pipe, here is the velocity v, okay, which is the average velocity, and the length scale here is d. The average shear stress that is associated, the average shear stress that is associated with the viscous flow or the viscous shear stress is mu v over d. Okay, so it's a comparison. Reynolds number is really a comparison between rho v squared divided by mu v over d. Okay, if Reynolds number is much smaller than 1, this implies the denominator is much larger than the numerator, or viscous effects dominate over the inertial effects. Okay, if Reynolds number is on the other hand much more than 1, this implies inertial effects dominate over viscous effects. A Reynolds number that is closer to 1 represents inertial and viscous effects that are equally important. Okay, so if you consider pipe flows which have velocity of some value, they have a density mu and viscosity v and diameter d, you can always calculate Reynolds number. If this Reynolds number turns out to be much less than 1, this means it's a very viscous flow, and examples of those would be, let's say, like flow of honey or shampoo, okay, or very thick oil, okay, or pancake batter, and so on. Why are these flows very viscous flows? These fluids typically have density that are high. Density that are high, but also their viscosity is very high. Okay, that will make Reynolds number, which is rho Vd over mu, much smaller than 1. Much smaller than 1. It is also true, Reynolds number is also much smaller than 1 for flows around microparticles. Like if your particle size is very small, then Reynolds number will obviously be small as well. Okay, that's an example of a low Reynolds number flow. The Reynolds number is much more than 1 if usually the velocity is high. If you have a pipe flow, let's say your pipe diameter is about 1 feet or 1 foot. If the velocity is high, if your fluid is, let's say, air, rho mu for air, rho for air is around 1.1 kg per meter cube. Viscosity for air is around 10 power minus 5 Pascal second. And if your velocity is pretty high, if your velocity is even a few meter per second, then your Reynolds number could be more than 1. Okay. Now coming back to pipe flow, there is a certain scaling with the Reynolds number, and if your Reynolds number is much less than 1, it's definitely a laminar flow because viscosity dominates, making the flow nice and orderly. Okay. Okay, if in the same scaling you have your Reynolds number, here is 1. If your Reynolds number is more than 1, doesn't mean it's turbulent or doesn't mean it's not laminar. In fact, for pipe flow, it has been empirically found that until about 2300, which we label as Reynolds number critical, the flow is laminar. That is based on the density, velocity, and diameter and viscosity of the fluid. If the Reynolds number is less than 2300 for pipe flows, then the flow is strictly laminar, always. If the Reynolds number is more than 2300, then it doesn't mean it's necessarily turbulent, it could be turbulent. If you have a pipe that is very smooth on the inside, there is no disturbances, there is no bumps, there is no irregularities. If it's a very smooth pipe, the flow could remain laminar until even 10 power 5. Even 10 power 5. But usually there is a transition, or there is a certain Reynolds number beyond which it's very difficult to maintain a laminar flow, and generally as Reynolds number increases, the chances for turbulence increases. Okay, and beyond about Reynolds number of 4000, usually the flow is turbulent unless someone takes extraordinary precautions to avoid turbulence, and this is described in figure 8.11. Okay. Now if you think of a laminar flow, okay, if you think of a laminar flow, think of a point. You have your velocity at a point. The velocity is usually if you put a velocity sensor here and actually measure it as a function of time, you get a velocity that is nice and steady. That is, at that point velocity is steady, doesn't fluctuate. It may change over time. That is it may change smoothly over time, but within that, if you take the velocity itself, there is no fluctuation about the velocity. Contrastingly, if you take a turbulent flow, the velocity at that point in a turbulent flow is composed of not just a steady portion but also a fluctuating noise component. So there is the velocity u at this point, which is composed of a mean or a steady component and a fluctuating component. The fluctuating component is what makes turbulence what it is, and it's quite important because it transports momentum across the flow by means of these fluctuations. Okay. Now, if you think of the turbulent flow, you can write U to be a steady component plus a fluctuating component. Now, what is the kinetic energy of this flow? That is, if you think of what is the value of U dash, if you, let's say, calculate the average value of U dash, you can write this, by average I mean a time average. How do you write the average of some quantity? Let's say you are having U dash plotted here, and these are all different values of U dash. You would take the average, you would take the average value of U dash to be sum of all the U dash measured, okay, divided by number of observations, right? I can do the same thing, express this in an integral form as over T naught to T naught plus T U dash dt divided by T. Okay. Now, what is U dash? I can use this relation to substitute for U dash. This is T naught to T naught plus T U minus U bar dt over time. Okay. So I have the average value of U dash to be 1 over T naught to T naught plus T U dt minus U bar dt, and I'm going to split this. I'm going to write this 1 over T naught to T naught plus T U dt minus U bar, which is a constant, from T naught to T naught plus T dt, the whole thing divided by time. Now, this quantity here is the definition of the average velocity. This is the time average velocity. That it includes both steady and unsteady parts. Okay. So this quantity is U bar. This quantity here is U bar times T. This quantity here is U bar times T, and this quantity here is also U bar times T. So what you are getting here is really the average value of the fluctuating component is 0. That is, if we plot the U dash, it's about 0. It is such that the area above and the area below 0 they add up to exactly 0. Okay. That is, the average value of the fluctuations is 0, but if we take the product of the fluctuations and then take their average, what you would get is that this is T naught to T naught plus T U dash squared dt. This is a quantity whose value is going to be at least, or it's going to be more than 0. It's always positive. And this quantity here, u dash squared square root divided by u bar, is called the turbulence intensity. It's called the turbulence intensity. Obviously, this will not have any unit. It's a percentage. It's like saying the flow has a mean velocity of 1 meter per second. It's like saying the flow has a mean velocity of 1 meter per second and a turbulence intensity of 1%. That would mean u bar equals 1 meter per second and u dash squared square root, the whole thing, divided by u bar equals 0.01. That's the that's the meaning of that statement. Turbulence intensity of 1%. Okay, u dash squared, the whole average time. Let me just rewrite this a little so that there is no confusion. U dash squared, average of that and the square root of that divided by the average velocity. That would be 0.01. Okay. Now for a laminar flow, the shear stress is mu times du divided by dy. Okay. For a turbulent flow, this shear stress is expressed as mu times the gradient in the average velocity minus rho times u dash v dash, the whole average. This part is the shear stress due to velocity, due to transverse gradient, due to transverse velocity gradient. This term here, u dash v dash, the average, u dash is the velocity fluctuations, or u dash is the fluctuations in the x component of the velocity. Fluctuations in the x component of the velocity. Remember, u is u bar plus u dash. V dash is likewise the fluctuations in the y component of the velocity. V equals v bar plus v dash. Okay. Now rho u dash v dash, the whole average is simply rho times the time average of t naught to t naught plus t u dash v dash dt divided by time. This term is called the Reynolds stress, and in total the shear stress in a turbulent flow is the velocity gradient due to the average velocity minus rho times the product of the fluctuations in x and y component. This term is the additional shear stress that appears in turbulent flow. Okay, if you think of this as a laminar flow, u dash and v dash are 0, and this goes away, giving you back the original shear stress equation that we saw. Okay, moving on, we'll consider turbulent velocity profiles. That is, in a laminar pipe flow, we saw that the velocity profile is parabolic in shape. Okay, here is your wall, which is at 0 velocity, and here is your center line, which is at Vc, the maximum velocity. And you do know that the velocity as a function of position scales as r over r squared. Okay, it's a parabolic velocity profile. In a turbulent flow, it's very hard to calculate the velocity profile from simple theory. Often it is measured. So in turbulent flow, velocity profile is measured because computation or calculation is not easy. Simple. Okay, and what we do is we fit a function for the average velocity as Vc divided by 1 over r minus r the power to the power 1 over n. This is equation 8.31 in the book. It's equation 8.31 in the book, and also figure 8.18. Figure 8.18. Figure 8.18 also compares the shape of the velocity profile for different values of n. Obviously for laminar flow, we had r over r squared. Okay, and n can take different values like n equals 6 to 10 for different turbulent flows. Okay, figure 8.17 plots n versus Reynolds number and gives you the values between 6 and 10 for different Reynolds number, and these are all based on experimental data. Okay, the experimental values are fit to these functional forms, and we'll see some examples during lecture time.